Wobbly, episode 48, Wobbly Stars and Exoplanets. And we're back for another episode of the Syzygy podcast. My name's Chris Stewart. I'm sitting here at the table with Emily Brunsden here in her office once again. Hi, Emily. How you doing?
Hello, hello.
So today, well, in a funny way, this episode's all about you, Emily, isn't it?
Always all about me, isn't it?
Well, that's true. You are the most important part of this podcast. But more specifically, your area of research. We talk on this podcast quite a lot about a burgeoning area of astronomy in the modern era, which is exoplanet astronomy. Like, you don't have to go back terribly far before the whole notion of exoplanets is, well, we think there are probably planets out there somewhere, but we only know about the 9 or 8 that we have in our own solar system. But turns out, and in fact the Nobel Prize this year went for some of these discoveries, turns out there's a lot of exoplanets out there.
There
Quite
are
a few.
A lot. About 4,000 we know of now.
And they're the only the ones we know about. I mean, you said a stat a number of shows ago, which was something like, what ridiculous proportion of stars we think probably have planets around them?
Well, we think basically every star in our galaxy
So
has
all
a
of them.
planet.
All of them.
On average.
So what that means, some of them have none, but some of them have lots.
Yes.
That's a lot of planets, right? So this is a big thing. But because they're planets a long way away, they're really hard to investigate. They're really hard to find out about. And some of the ways that we have to learn about the exoplanets are more accurate than others. And it turns out, Emily's been telling me, that people who study stars actually have a lot of influence over what we know about planets. So we're going to dig into that today. This is Emily's area of expertise. I'm going to hand over to you, Emily. What are we talking about?
Yeah, well, so I wanted to, this is actually something I mentioned, I think, all the way back in one of our very early episodes when we did, of course, my favourite field of astroseismology.
Yeah.
And I sort of made an offhand remark at that point, which was kind of, well, astroseismologists turn out to be the best at measuring planets. And you said, hang on a minute.
That doesn't make
sense.
sense.
How does that work?
What
You're
are you
doing
talking
stars,
about?
not planets. Are you aware that they're different things, Emily? And yes, I am very
I
aware.
hate to take you to school on this one, but even I know that, okay?
But it turns out that the two communities of astroseismology and exoplanet hunters work very, very closely together. And I kind of wanted to give a few examples of the amazing stuff that's been coming out over the last couple of years because of that collaboration.
Okay, so we're going to need to, as we often do on this show, we've got some stuff to unpack, right? Let's start with astroseismology.
Yeah.
What's like seismology, earthquakes, so space earthquakes?
Sort of.
What?
It's actually astero with an E, which is
Astero. That's
Yeah.
different.
so that it's ER, which is actually important. The E matters. The
The E means something.
does mean the E tells you it's to do with stars, actually.
Ah, there you go. Do we find that anywhere else? Are there any other astero words?
Yeah, lots of Latin root words and,
Right.
and like asterism and things like that. Asterix.
There you are. I never thought of that. There you go. Learned something today. Asterix, it's a star-shaped thing.
Yeah.
Huh. There you are. And asterisk for the symbol and asterix for the small Gaul character in the comic books. Anyway, astroseismology. So this is starquakes,
Yes, exactly.
not just spacequakes, but
Yeah,
star.
so we're looking at basically coherent pulsations in stars. So the surfaces of the stars are moving in some kind of global coherent way, and those pulsations are regular, and we can study them, and we can measure them, and we can use them to get all sorts of really amazing information out of the star.
Because stars are basically big, blobby things filled with energy, right?
Yes.
And so big, blobby things filled with energy can get all sorts of interesting, specific kinds of wobbles in them, and
Exactly.
you can measure them. How's that? Does that sound like a thesis?
That's a really good thesis.
Excellent. All right. So that's great. Fantastic. Well done. We can learn all about stars from the way they wobble, but we're not talking about stars today. We're talking about exoplanets. So help me make this link. How do we get from one to the other?
Well, if you look at how well we can actually measure exoplanets, and this is the two main properties you might want to know about an exoplanet. You want to know its mass and you want to know its radius.
Yeah, I mean, that's a really good start. Ideally, we'd like to know whether or not it's got, water and life and swimming pools and frogs and ducks and things. But let's start with mass and radius. Surely they're the easy ones, right?
Yeah, well, we can get those numbers, but getting them accurate is super difficult.
Okay.
So we'd like to get them, for example, better than 10% accuracy.
Ideally, I mean, a 10% accuracy is, that's not great, but at least you know you're in the ballpark. Like that's your ballpark figure. That's your order of magnitude. It's this plus or minus a bit. Yeah?
Yeah.
Yeah.
And those errors are really, really important because with, even at the 10% level, you're talking about, quite a substantial difference in whether what you end up, your density of your planet would be, for example.
I mean, at the 10% level, if something measures 10, then it might, a 10% error might be 11, it might be 9, somewhere in that region around 10. That's still a fairly significant uncertainty.
Yeah.
But you know that you're reasonably close. Yeah, so you want at least that.
But it turns out that our ability to get those numbers is, for the vast majority of exoplanets, we're above that 10%. And for many of them, we're above 50%, above 100%.
Wow.
In terms of errors.
50%, 100% errors, as in, it's got a mass of 5 and it might be as big as 10. It might be as small as 1 or less. Wow.
Yeah.
Okay.
Yeah.
Basically, that's saying we're pretty sure there's a planet
there, and we don't really know much about it.
Yeah, and so mass and radius, you've got similar kinds of.
Yeah, one of them radius is slightly easier to nail down the mass, but it's all based on basically how well you can measure the star that the planet is going around.
Right.
So if you've got massive uncertainties on how good you can measure your star, then those transfer to how well you know your exoplanet.
That makes sense, right? Because these measurements are only as good as your least good measurement that feeds into it. So if you can't measure the star particularly well, then you've got Buckley's chance of figuring out what the planets are doing.
Yeah.
Fair enough. You can see that they're there.
Yeah.
There's no question. But what is it? Where is it? How big is it? No idea.
So these measurements are really, really hard. But fortunately, we've got a field which can come to the rescue here.
And it's coming to the rescue by saying, well, you know what? If you want to know about the star, we can tell you about that.
So it turns out that astroseismology can help.
Mm-hmm.
We can routinely get errors down to less than 5%.
That's good.
For stars.
That's good. I mean, heck of a lot better than 100 or 50 or even 10. That's a big improvement.
Yeah. So that gets us below 10% in mass, and it can get us down to even something like 3% in radius.
And in this kind of field, like in some fields, 10%, 5%, 3% would be embarrassingly bad. But in other fields, that's actually extraordinarily good.
Yeah, there's ongoing jokes in astrophysics generally that order of magnitude errors are kind of viewed as good.
Yeah. Yeah. I mean, it comes down to that sense of, look, but we can see that they're there at all, like pat on the back all around just for knowing. Okay, so you can really narrow this stuff down. How does that work? So,
we use very particular types of stars. And so there's kind of 3 different areas of planetary science which have really evolved and astroseismology can make a huge contribution to. And these are areas where we're looking at those 4,000 exoplanets or subsets of those huge numbers of exoplanets. And we're drawing out patterns. And if you're going to find patterns in data, it's very, very difficult to find patterns if your errors are very, very large. Yeah. I mean, the whole notion of patterns is being able to look at a very large data set and being able to see which ones are going in this direction, which ones are going in that direction. What's the lay of the land? And if the entire lay of the land is fuzzy, you can't see much. No. It's very difficult. So this was first really brought to light in a Nature paper that came out in 2016. It was by a whole bunch of astroseismologists, basically, and some exoplanet people. Who sticking their flag in the ground and going, this is ours. Yeah. Pay attention. The author list is kind of a who's who of my last conference. So it's by Lundqvist et al. And what they did was they took the data that they had for more than 100 astroseismic measurements of stars and used that to really narrow down the error bars of what the exoplanets were doing. And they were able to find something which we now call the hot Neptune desert. The hot Neptune desert. Talk me through that. Well, confusingly, it's also sometimes called the hot super Earth desert. But we've encountered this one before, haven't we? We've sort of got mini Neptune, super Earths. It's this gap that we see in our own solar system where there isn't really anything in between Earthy, Marsy type sized things and Neptune-y type things. There's a gap there. So here you're talking about the hot Neptune desert. Yes. Okay. So all these planets that sit between the mass and radius of Earth and Neptune. Mm-hmm. And remind me again, how big is that gap? So how much bigger is it's quite big. So if you Neptune think about an Earth's masses, you're talking about somewhere between sort of 2 times the mass of the Earth up to maybe like 14, right? Something like that. Okay.
Okay.
Yeah.
So I can think in my mind's eye, we're talking something like 10 times the size of the Earth-ish.
Yeah.
That kind of thing. As opposed to Jupiter, which is just much bigger.
Yeah, which is something that we don't have, obviously, in our solar system.
Yeah.
But one of the most remarkable results from Kepler was found that this kind of band of planetary sizes is the most common that we have in the galaxy.
That's right. Huge numbers of them. We didn't see them initially because all we saw was lots of big Jupiter-y things because they're the easiest ones to see. But then turns out, no, hang on, there's all these things. We don't have them in our own solar system, but there are plenty out there in the universe.
Yeah.
Okay, cool.
So the most common type of planet in our galaxy is a super Earth or a mini Neptune, depending on which way you want to go, up or down. And that definition's a bit hazy, but
great.
Somewhere
Let's just be comfortable with that ambiguity. That's fine.
Yeah. Okay. So now we've got a hot super Earth, let's say desert. And what that means is if you do a plot of how hot a particular planet is, and that's based on how close it is to its host star, it's also based on how bright the star is. So if you think just Earth is nice and Goldilocks zone, good temperatures, 0 to 100 degrees Celsius. We're warm and cozy here.
Yeah, we like this one.
Yeah. So this is our kind of base temperature range. So if you did a plot of kind of this base temperature of other planets and you look at that compared to their mass, there's a hole in your diagram, which is where these Neptunes that are warm, or sub-Neptunes that are warm, should be.
Okay, so just take me through that. Explain that a bit more. So, is what you're saying that like we're looking at two different things here? We're looking at size of planet, like mass, radius of planet, and we're talking about basically where they are in relation to their star, how close, how hot they are. They're not really long way away in the freezing cold of space, way away from the star. Are they really, really close? And you're saying that there's a gap in that. If you sort of plot that out, there's a bit of a gap there where you would expect these Neptunes to be.
Yeah.
These would be Neptune-sized planets closer to their star.
Yeah. So
and they're not there.
To put another number on it, you can say that these are things with periods of, say, 2 to 4 days.
Right.
So super close, which means they're very, very warm, and they're kind of in this range, somewhere in between Earth and Neptune. So they're just not there.
Right. And we'd expect them to be there?
Well, didn't necessarily begin to think that they might not be, at least from our initial ideas about what the overall distribution of planets in the galaxy might be.
Okay, so if you were to just wade in and naively say, okay, bunch of planets spread out like this from very, very small to really, really huge, and they can be anywhere from incredibly close to the star to really, really very long way away from the star, we didn't have any reason to think a priori that you wouldn't have Neptune-sized things in this kind of proximity to the star. And they're not there, and that deserves explanation.
Yeah, because you've got bigger things and you've got littler things, right?
Okay, so you've got big things close to the star, like Jupiter-y things.
Yep.
And you've got little earthy, Venus-y, Mercury type things, but you haven't got anything in between. And that is odd. Because if it was just, you only ever find tiny little hot rocky planets close to the sun. Oh, okay, all right, we could come up with a reason for that. But why not the middle-sized ones? Where'd the middle-sized ones go? That's the gap.
That's the gap.
Gotcha. Right,
But
I'm with you.
to find the gap, we needed to get much, much better at doing the measurements.
Right. So this is where those error bars come in.
Yes.
Right? If you don't know how big your planet is in mass or in radius, then you can't be sure if there's a gap or not. So, there might be a gap. Kind of looks a bit gapish, but it's all very hazy because the error bars are so big. We don't really know how big these things are anyway.
Yes.
Okay, so we're nailing down the uncertainties in those masses and radiuses, and turns out there's a gap.
Yeah.
Right.
It magically appears when you basically get your data to be very, very precise.
Turns out. Who'd have thought?
It's fantastic. So this has allowed us to study, since this discovery, this desert basically in a lot more detail and start to put together some models that also explain the same thing. So the idea is that if you're a very, very large Jupiter-sized thing with a big, big atmosphere, you probably didn't form where you are close to the star. Probably you migrated in at some point. But the fact that you've got a lot of mass means that you can hold on to your atmosphere.
Right, because you're already very massive. You're dragging all your stuff along with you. It's going to be much harder to influence you, even if you are close to a star.
And the sun, or the star is pushing atmosphere off and evaporating atmosphere off. But if you've got a lot of gravity holding it on and you've got a lot of atmosphere to begin with, then that's probably not a significant effect.
Sure. Okay, so I can see that. That makes sense.
Yeah. And so now if you take something that's kind of a bit more middle-sized that still has a chunky atmosphere, because remember that Neptune and Uranus have large icy atmospheres, right?
Right. Okay. Yeah.
So-
Tell me a little bit about the structure of a Neptune. What's it like?
Well, we don't know a lot. It's got a core in the middle,
Okay.
and a big atmosphere. It's mostly sort of hydrogen based, and then some molecules on the icy.
Like I'm
molecules on the
imagining
outside.
something which is like, how big is the core in relation
That's
to
a good
the
question.
radius? Like, is it quite a small thing with a really, really thick atmosphere, or
I
is
think
it?
our best understanding is it's relatively small compared
Right.
to the atmosphere.
Okay, so it's a bit of a ball in the middle and then this big atmosphere around the outside. Okay.
So if you take that and you push that in next to a sun, it doesn't have the mass that a Jupiter would to hold on to it gravitationally. And at the same time, you've got photoevaporation, so light from your star is evaporating off your outer atmosphere. So it probably doesn't last very long.
Yeah, you've got less of it to begin with, so you'd notice it going much faster, and you're not hanging onto it as hard. So that's going to go relatively quickly, which means you wouldn't find many of them around,
Yeah, because you'd just be left with the rocky lump in the middle.
which is what we see. We see the little ones, and we see the big honking Jupiter-y ones, and we don't see anything much in between.
Well, except that we have found one, of course.
Right. Well, I mean, there's always an exception.
There's always one. And this was quite cool because this came just a few months ago, in May this year, May 2019. So this was a piece of work by West et al. From the University of Warwick, who found this planet. It's called, wait for it, NGTS4b.
I don't get surprised by these anymore. Well done.
We'll just pass over that one. 20 Earth masses, so it's a bit bigger than the Earth, and about 80% the radius of Neptune.
Right.
So it's kind of just a sub-Neptune.
But it's hot. It is
But
in
it's
close
hot,
to the star.
yeah. So it only takes about 1.3 days to go around its host star, and its surface temperature is probably about 1,000 degrees.
Wow. Okay, so that is pretty hot.
It's pretty hot.
So by your previous description then, my guess, and it's a guess because I don't know what I'm talking about, but my guess would be that it would be in the fairly early stages of having its atmosphere ripped off it by the radiation and the solar wind coming off that star. That if we were to look in, I don't know how many years, millions, billions, it wouldn't be a big planet anymore. It would be a little planet.
That's certainly one explanation.
Right.
Yeah.
Okay.
So this one's actually called the Forbidden Planet, which I call
Ooh.
because it sits in this gap
Oh,
where
I
it
like
shouldn't,
that one.
shouldn't be. So it's the Forbidden one.
Sits in there waving at all the astronomers going, I'm an exception.
Yeah. There's an exception for every rule,
Yeah,
isn't there?
that's the great thing about astronomy.
Yeah, so like you say, it could just be that it's migrated in very recently, and much more recently than the star has been sort of calming down. So it's probably not had much of a time to photoevaporize. Or, that's a word, right? Photoevaporize.
Sure. Yeah. Coin that one. Done.
Or perhaps it's actually got a higher core mass than usual.
Okay. So it's hanging on to its
bit-
atmosphere a bit harder.
A bit stickier, kind
Yeah.
of, yeah. So that's really
Cool.
cool.
Yeah.
But the only problem with this planet is it's about 922 light years away,
Right.
which means it's actually super hard to detect and super hard to follow up.
Hang on. 922 light years. Is that a long way?
That's
from
quite
these-
a long
for
way
these
for an
things?
exoplanet.
Is
I mean,
it? Okay.
well, yes and no. We're good at detecting a lot of planets very far away from Kepler, but it's only with TESS and ground-based observatories that we've been really hammering the closer exoplanets.
So what kind of distance would you be looking for a typical exoplanet that we would be studying like this? So if 900 is a long way.
Ideally, we'd like ones that are in the tens or hundreds of
Right.
light years, so
Okay.
in our local neighborhood, because then we can follow them up and we can do things like spectroscopy with them,
Right,
get
right.
like lovely atmospheric measurements that James Webb will be able to do, all that kind of stuff.
See, my problem is that this podcast is messing with my concept of what's big. And when you first start looking into this stuff as a non-astronomer, everything's huge. The moon is an extraordinarily long way away, so nothing is surprising. And then you get used to it, and you think, oh, it's just across the galaxy. That's not even outside of our local cluster. Like, come on. And so then you start asking questions like, well, how far away is an exoplanet that one might like to study with the techniques that we have? So I have no idea. I haven't got the foggiest. Is it hundreds of thousands of light years? I have no idea. Okay, so now I have a mental image. Hundreds. A couple of hundred light years. Sounds about
That'd
right.
be perfect.
Yeah,
Yeah.
cool.
Yeah.
Okay.
So that's what TESS is really focused on doing, is finding all these wonderful targets that are in our local neighborhood.
Cool. Okay, so you said that there were three things. That's the first.
That's the first one. So that came out in 2016.
And what was that? That was the hot Neptune desert.
Yes.
Awesome.
Yeah. So we're going to move on now to another good one, which is the radius gap.
The radius gap. It's not, I don't know. It's not as sexy as the hot Neptune desert.
It's not, but this one does have a better name as well. It's also called the Fulton Gap.
Okay. All right. We'll go with it.
Well, the story's quite good with this one because it was discovered by a guy called Benjamin Fulton, and this goes back to 2017, who actually put it in his thesis.
His thesis. So this was like day one of his research career. Nice work.
Exactly. I mean, how amazing is that to have not only, these wonderful nature papers and so on come out about your work when you're a PhD student, but to have something named after you.
Get an entire gap named after you. That's pretty good.
Fantastic?
I mean, I had a couple of papers out of my PhD, but no one named a gap after me.
No.
Nice one.
Yeah, good work. So the Fulton Gap, this is just basically we haven't found anything that has a particular radius. So this is a gap if you just plot all the exoplanets we know and look at their radii. So
hang on. This is not sort of closer to the star, further away from the star. This is just saying, look, we have planets and they have radii anywhere from very, very small to really, really quite large. And you're saying that there's a gap where we don't find any. And it's not sort of, we don't find any which are smaller than, a marble. We don't find any which are larger than a red supergiant star. This is somewhere in the middle range where there aren't any exoplanets of that radius.
Yeah.
Okay.
Yeah,
right.
There's just a gap.
You have piqued my interest. It didn't have such a great name, the radius gap, but weird. Go on then.
So the gap is somewhere between 1.5 times the radius of Earth and 2 times the radius of Earth.
Now in a way that doesn't sound much because we were just talking about Neptunes, which were sort of 10, maybe 20 times the size of Earth. And so 1.5 to 2 doesn't sound like much, except that when you think of that in terms of a percentage, like going from 1.5 to 2 is a big jump.
It is, yeah. And imagine what your 10% errors are like on this.
Yeah.
So 1.5, you're talking 10% is maybe between 1.4 and 1.6.
Yeah. So that's significant. So that really is a gap. That's just not sort of, don't worry about it. It's not a big deal. We'll find one eventually. No, we should see things in there, and we're not.
And when you've got 4,000 exoplanets,
the stats are starting
you're getting suspicious.
So, okay. Why? How?
It's interesting, this one. So we think it's either one of two things. It could be to do with the formation of planets. So unfortunately, we don't have anything that's like this super Earth in our solar system. So it's harder to make models. We don't have the same volume of data. But maybe during the formation, there's just a sort of size limit that you just seem to either whiz through or can't get up to. There's kind of some barriers to formation there. Maybe it's to do with composition. So depending on where you're going to sit and what distance from your star you sit does influence how big you get, right? There's no coincidence that all the biggest planets in our solar system are out beyond the asteroid belt, for example, Jupiter and Saturn. They're out there because they could hold on to the primary hydrogen and helium that was sitting around in the solar system.
Yeah, it's a process that we were just talking about with the Neptune gap. The hot Neptune gap was, the star's going to blow away your outer atmosphere unless you're big enough to hold on to it, which is why you only find the big ones further out. That kind of makes sense.
So maybe there's just no way you can build this kind of composition in the inner part of the solar system, which is where you'd have to be to have this kind of mass. Or maybe it's something to do with the way that planets cool. Maybe they sort of start off with a kind of a random distribution of masses, and the ones that are this size tend to cool down. When the cores cool down, they contract, and they're only able to hold on to a particular size of atmosphere.
Right, yeah, because we're not talking about mass here, we're talking about radius. Yeah. Right. Okay. So those are all plausible things, but it's interesting.
It's very interesting.
And it's the only... Again, coming back to the whole reason that we're talking about all of this, the only way that you could identify a gap like that is by nailing down the mass and the radius much better, which one can do through astroseismology.
Yeah.
Awesome.
Very cool. And then there's a very more recent gap, if you like, that's been found. So
Another gap.
I found a couple of papers referencing this over the last few months. So June, July 2019.
So this is really recent.
Yeah. This is quite exciting stuff. So this is looking at what they've now termed impossible planets.
Hang on, we had a forbidden planet. That's bad enough. Like, I'm sorry, you're not allowed there. But no, you guys are actually literally impossible.
Impossible.
Okay, what's an impossible planet?
So an impossible planet is basically if you do a plot of your mass versus the period that you have going around your star, then it seems to be that there's a diagonal line which fractures your plot into two different clumps.
Okay.
So you get the bottom left, which is things that are kind of low mass and low period. And you get the upper right, which is kind of high mass and long period.
Okay.
And we see that in our solar system, right, as well. You know, again,
Sure.
the bigger things are further out.
Mercury's really close and Jupiter and Saturn are a long way out.
Yeah.
Yeah.
And there's lots of exceptions that we found. You know, you can find all the things across this diagram, but there is really an appreciable valley in the middle that you can really just not see any type of planet in.
Okay, so what, in terms of what you just described then, of the little ones being close and the big ones being further away and all of that sort of thing, how would you characterize an impossible planet, one right in that chasm?
So it has a particular mass that cannot have that period, or equally a period that cannot have that mass.
Right. And that's something that we observe, or there's a reason for that?
So it's just an observation at the
Right.
moment. So it's based on quite a lot of work being done with mostly sort of intermediate to low mass planets. So things that are 25 times the mass of the Earth
Okay.
and less. So we're not really including the super huge ones because they drift around a little bit, I guess.
So this is where the stats are really starting to crank up. That in the previous gap, who was it?
The Fulton Gap.
Fulton Gap, that's the one. In the Fulton Gap, it was, you just don't find planets of this radius, between 1.5 and 2 Earth radii. You just don't find them anywhere, okay? Fine. This is taking it kind of to the next level, which is, well, if we look where the planet mass and radii are distributed and their orbital periods, then you don't find these kinds of things in these kinds of orbits generally. There's this big gulf, and you could only get that from much better statistics, really sort of being able to pull apart where are the planets with particular radii, what are their orbital periods, and so on. You really need a lot of stats for that.
You do. And we don't have a lot of information about why this particular straight line, if you like, this gap should exist. The study that I saw was from Armstrong et al. From Warwick. And they'd tried lots and lots of different ways to plot the data. They tried radius, they tried mass, they tried temperature, they tried star, they tried lots of different things. And really all they could conclude was that it's probably something to do with the atmosphere of your exoplanet. And maybe it's a formation-based effect. But we haven't got a lot further than that just yet.
So it's a lot of speculation going on there. So what you're saying is that there's some kind of relationship between the formation of those planets and the size or the way that they're forming in a particular, distance away from their star in a particular orbital period. There'll be an interplay there which says, yeah, you know what, you just don't tend to get that.
Yeah, well,
Yep.
It's impossible.
It's
perhaps.
impossible. Yeah. Now, you said before that in the forbidden zone, there was actually one sitting there waving at us. Are there any impossible planets?
Not that I'm aware of at this point. I'm probably sure there will be.
Guaranteed
if we
there will
haven't got
be,
one now, there will be one.
Because there always are.
But yeah, again, I mean, this is the difficult thing with exoplanets is you're trying to use what you see now to work out things like formation models. But exoplanets can wiggle around in orbits, and they do these beautiful dances, basically, depending on how the mass distribution in the whole system can change. So you can move big things out, but those don't have isolated effects.
Yeah.
If you move Jupiter, like Saturn probably pushed Jupiter in a little bit at some point during our
Yeah, and those big planets
formation.
coming in and going out, that'll have a huge effect on everything else.
Yeah, it's a big dance.
I remember you saying that the early solar system was probably very different from what we see now. And what we see when we look at all the exoplanets that we've discovered so far, all 4,000 plus of them, will be in all sorts of different stages of system evolution, I guess.
And there's no reason to believe that captured planets don't exist, for example. That
Something just winging on past and going, gravitational, I'll just be attracted to you, thanks, and I'll suddenly become a planet.
Yeah, so there's lots of complexities in these systems, basically, that we have to think about.
Yeah, so you're right. I hadn't really thought about that. But the fact that we're looking at them all now, and they're all within hundreds of light years, which means, when you look out into the sky, you're looking back in time. We've established that because light takes a while to get to us. But we're not looking very far back. We're basically, from an astronomical, cosmological point of view, we're kind of looking at now, effectively, because not a lot would happen within a solar system environment in hundreds of years. So we're looking in our local area at all these exoplanets basically as they are right now.
Yes and no. I mean, there are lots of really, really old stars and really, really young stars that we have found exoplanets. Because, yes, you're right. I mean, our sun was born at the same time as the stuff that was born out of the same gas cloud, if you like. But the rotation of the galaxy has kind of pulled that system apart.
Right.
So our twins, our brother siblings and so on that the sun was born with are distributed pretty weirdly across the galaxy.
Okay. So the stars that were formed from the same stuff that our sun was formed out of, that's not our local group of stars.
No.
That's sort of been spread out.
Yeah.
Okay.
Because it's basically like a motorway where you've got everyone going at different speeds as they orbit around the galaxy. So it's very easy to basically take off, and if you're in the fast lane, then you're going to lose the people in the slow lane pretty quickly.
So what you're saying is that all of the stars that we can look at and see these exoplanets and study these exoplanets, which are, none of them are terribly far away from us in the grand scheme of things, but they do cover a very wide distribution of old stars, new stars, systems that have evolved a lot, systems that are only just starting to evolve.
Yeah.
And our stats with enough of those can start to build up a picture of evolution of planetary systems.
Yes, that's the idea. And I'm glad you mentioned this because it turns out that astroseismology can come to the rescue once again.
Hurrah! We've already had 3, add in a 4th.
So this is very early stuff, so I don't have a lot of kind of new
because
research
a couple
to
of months
report
ago
this.
is ancient history.
Yeah.
But this is paint still wet on this one.
Yeah, I haven't got any papers to quote in here anyway. But basically, astroseismology can put precise ages on stars as well.
Okay.
So we're good at mass and radius, but we're also really good at age.
How does that work?
So what we can do is work out the interior compositions of stars, and we can do that very, very accurately. And a star's interior composition changes as it ages. So if you want to age a star, astroseismology can do it to around 10%.
Which, again, that's quite a big uncertainty, unless you're going against something which is, well, previously we had no idea at all.
So I'm just going to go, this is phenomenal. This is huge, being able to age a star to 10% accuracy. It sounds like it's same as mass and radius. It's actually a much, much harder observation to do.
Right.
For just a general star that you see. And that's because basically you're modelling. You're saying, well, these are the best sets of physics that we have to describe how a star moves through its lifetime. But just knowing the age and the radius doesn't tell you anything about how old a star is.
So if I can sum up the mental image that I have in my mind of what you're talking about in your field, you have a star. It has an internal structure which is based on not only what's happening now, but also how the systems within a star evolve over time. You have set up within that star, as we said, it's a big blob of stuff and it wobbles, and you've got some very specific wobbles that you can measure to the very best of your accuracy, and you're modeling the way that those wobbles tell you about the internal structure, but also modeling the way that structure evolves over time. And you're telling me that you're able to do all of that and be able to date the age of that star to 10%. Well done. That's pretty good.
It's amazing.
That's pretty good.
Yeah, our best estimates were at least 100% before that.
Really? So sort of, 10 plus or minus 10. It's a star. We know it's there.
Exactly. It's really, really amazing that we can do this.
Yeah. Wow. Well done you.
Yeah. So now that we're on that a massive high, maybe we should just kind of wind these gears back a little bit.
Hang on, I'll take that trophy back. Yeah.
And maybe talk about a little bit the limitations about what this technique is for.
Yeah, okay. So it can't do everything, is what you're saying?
Unfortunately can't do everything.
Okay, so hang on. Let's just sum up. You're able to do all these amazing things, age the star, get a really good grip on the mass and the radius of the star, which gives you a really good grip on the mass and the radius of the exoplanets, which can then help us to really narrow down these stats to tell us that there are some planets that just don't exist, some planets that seemingly can't exist in particular orbits and in particular masses and radii. You can't do everything. So where are your limits?
Well, our limits are we can't do every star.
Ah, okay. Is that because not all stars wobble?
It's exactly this point. And in fact, it's worse than that. Not all stars wobble in this very specific way that we're very, very good at making these measurements.
Here we get to the heart of science, isn't it? Which is, do you know what? We really, really understand this incredibly limited scenario extraordinarily well, and everything else is a mystery to us.
Yeah, that's pretty much it.
Yeah.
So when I say astroseismology, this is actually a branch of astroseismology which has had an enormous amount of success over the last few years. And this is looking at solar-type oscillators.
Okay. Tell me about solar type
So
oscillators.
the sun has oscillations on
Right.
its surface, and these are very, very low amplitude oscillations. We've only really been able to measure them super well over the last couple of decades. And these are what they're driven by turbulent convection.
Okay, so
Let's pull that apart.
Pull this one apart. We're talking about the sun
Yep.
at the moment, and the sun has oscillations, vibrate waves.
Yep.
Waves, let's call them, on the surface, around the surface going up and down.
Basically traveling around the surface.
Right.
Yeah.
Okay. So, a little bit like the way, a wave will travel across water. These are waves going around the surface of the sun.
And they really are kind of surface waves in that they don't go particularly deep into the solar interior.
All right. So it's not the whole sun sort of squashing and expanding and wobbling around like that. It's waves on the surface.
Yeah.
Cool.
And very specifically, it's in the convection zone of the sun.
Tell me about the convection zone.
So this is the outer layer that we can kind of see with this, we call it the photosphere. And this is basically like a pot that you put on a stove. You've got hot things at the bottom that bubble up to the surface and sort of blow into little bubbles on the surface.
So this is the rolling boil of the surface of the sun. It's hot bits coming up to the surface, cooling down a bit, going back down, but not terribly far down. You're saying this is sort of an outer surface layer, and you're getting waves in that.
Yeah.
Okay.
Yeah. So they're sort of pressure waves that are driven by this convection, and using that information, you can make measurements. And we look at these solar type oscillators. Here's the kicker as well. Solar type oscillators are not necessarily stars that look like the sun.
Okay, I'm just wrapping my head around what the sun does look like, and now you're telling me that we can go and look at other stars which have solar type oscillators and they don't look like the sun.
They don't look like the sun because...
Why are they called solar type then? You people really need to think about your nomenclature.
They're called solar type because they're basically the same physics as what's happening on the sun.
Right. So it doesn't matter what they look like. It's the same sort of thing.
Yeah, so every star that you find that basically has the same properties as the sun probably also has these little oscillations.
All right, fair enough.
They're just so tiny we can't really observe them in many types of normal stars.
Okay.
Right? But where they become much larger, where we can see them, is in red giant stars.
Because they're very big.
Yeah.
Right.
So the atmospheres puff up in a red giant, and these oscillations come to such a height, basically, to such a magnitude that we can see them very, very easily.
Okay, so you've got an enormous star with an enormous sort of outer atmosphere anyway, and so you can get much bigger waves, is what you're saying.
Yeah,
they're much more easily observable.
They are, and they're beautiful.
And these things are huge, aren't they?
Yeah.
I mean, we're not mucking around. These are very, very large stars.
Yeah. So these are your Betelgeuses and things like that. Although I don't think we do have oscillations from Betelgeuse, but
anyway,
yeah, stars like that, big red giants. So these are solar type oscillators. These red giant stars have lots and lots of pulsations going on the surface at the same time, but they're all equally spaced.
Okay.
So in frequency. So this means if you see an oscillation, I'm going to speed this up a little bit, but if you see an oscillation at say once per day, which is a frequency, then you'll also see it at twice a day, 3 times a day, 4 times a day, 5 times a day, etc., etc., etc. They're equally spaced.
Okay, which, I mean, it's a little bit like a ringing of a bell. You're going to get certain tones and harmonics, and or a guitar string. A guitar string will vibrate at a certain frequency, but also a whole bunch of frequencies which are double that or triple that or quadruple that. That's the way things oscillate in their natural frequencies. Stars do that too.
They do, yeah. And the solar type oscillators are the most regular types of oscillators in terms of the frequencies that they excite.
Great, sounds good.
So that's fun.
Easy.
So you measure the spacing between all those frequencies, and that actually has a very deep meaning in physics, which is amazing. So it's called the large frequency separation, and it's basically with no other input apart from a bit of physics that you already know. There's no modeling. You can get the mean density of your star from that.
That's a pretty good get, right?
That's amazing.
That's a good measurement you can make, and you don't have to do any crazy modeling. You just have to say it's this.
Yeah. I mean, put that in context. Most of the other things that we know about stars, we have to use models to understand. We have to use the data that we have from very good stars that we've measured and basically generate a set of equations that will describe other stars.
Yeah, and that's not a bad thing. Like, we do modeling all the time in science, and it's incredibly reliable, but it's only as good as your assumptions and your data, and that can go awry. Models can be
and your
wrong.
simplifications, right, as well. Yeah. So if you can do things in a model independent way, not have to rely on them, then this is amazing because you're getting direct information.
Yeah, these are measurements and established physics.
Yeah, and as some of my colleagues love to remind us, stars are never wrong.
Well,
so if you're measuring it, it's
It's right.
The star is right.
You can-
no matter
you can
what
argue
you
with it.
want it to be.
You can argue with
the
it, but
star
you're
will
going to
be
be
right.
wrong.
Yeah.
Okay, so that all sounds good.
So you
Great.
get the mean density. And then if you look at the frequency that has the most power in it, so the most kind of highest
The
amplitude.
most dominant, yeah.
Yep. That tells you something about the gravity and the temperature of the star.
Great. So density, gravity, temperature.
Yep. And so you can combine them all, basically get the mean density and the radius of the star
Awesome. Good.
directly without a model.
That's impressive.
It's very, very impressive. And that's why our errors are so low, because we don't have to include all the errors from models. It's
Very
brilliant.
nice.
So this is how this works. But unfortunately, these types of oscillators are not super common in the sense of it's not every star that every exoplanet doesn't go around one of these red giant stars.
So what sort of proportion? Like
So the original study had something like 170-ish exoplanets.
out of thousands?
Yeah, I mean,
Yeah.
it was a couple of years ago, so maybe we were back at only a few thousand
Yeah,
then.
yeah.
But yeah, so we're looking at, fractions of
Right.
the total population of exoplanets go around these types of stars.
So it's going to take a while longer to get up the kind of stats that
Yeah.
you need. Yeah.
Well, yeah, so you can do this for a few hundred exoplanets and then extrapolate your data to the whole population. But what we'd really like to do is be able to use these techniques or similar techniques for all sorts of other types of stars. So all the others, basically, pulsators or not. But we haven't worked out how to do that yet.
So when you were talking a minute ago about the limitations, like, okay, so look at what we can do. Because you started this whole section that we've been talking about here with, yeah, but then there's the limitations. And then you told me something amazing, which is look what we can do. And it doesn't even involve models and it's amazing. And I'm looking at you going, well, that's fantastic. What's your problem? Oh, you don't know how to do all the other ones yet.
Yeah, it turns out to be less than 10% of the stars that we can do it with.
Damn it. Okay. Right. So you got a bit of work to do then.
Yeah, we're trying really hard.
And what do you think, as someone who works in the field, stars are not necessarily just going to divulge their secrets easily. The fact that you were able to do that with this particular kind of star and really get, model independent results out of it is great, but the universe doesn't always cooperate that way. So as someone in the field, like, do you reckon there's another one of those just waiting around the corner going, hey, 20% of the stars operate like this? Who knew?
Well, maybe. I think that might help a bit. I think if there were any more kind of really obvious relationships like this, we probably would have found them by
We
now.
would have tripped over them, yeah.
There's one interesting one which is coming out, which is about stars that are just a little bit hotter than our own, that are kind of more normal stars. These are called Delta Scuti stars. There might be some interesting relationships there that we can exploit to find out more information about these stars. But that's again only a small sample compared to the whole population. I think what's much more likely is that we'll be able to use these results and all the other partial clues that we have from every other type of star to build like a supermodel, if you like, that really contains the right physics, that contains the right numbers, that we'll be able to apply to the general population of stars.
Well, that's all the time we have for in this particular edition of the Syzygy podcast. I thought that was fascinating. I was really waiting at the end there, Emily, for you to just sort of say, well, we have our limitations. Basically, we can only do this in 0.001% of all the stars in the universe, and it's not nearly as exciting. And instead, what it basically came out with, yeah, but we're trying to get this supermodel of all the stars, and it's going to be awesome. And, that sounds pretty good to me, because there's a couple of things in there. A, we're learning more about the universe, and B, you're in a job for a really long time. So that's fantastic.
Yep, it's good news, isn't it?
Excellent. But we're going to have to wind this one up. Listen, before we do get out of here, we need to tell you about something very exciting that's coming up. In particular, if you happen to live in or around the vicinity of North Yorkshire, which is where we're based, we're in York, coming up on the 22nd, 23rd of November, there's a thing called the Podcast Social Club, which is a bit of a podcast festival for local and UK-wide podcasts on all sorts of topics. As far as I know, we're the only astronomy podcast that's involved, but we are involved, and we're going to be doing a live show on the evening of Friday, the 22nd of November. And we want you to come along.
Yeah.
You can just drive up if you're nearby, or you can fly in to somewhere local if you live a long way away and you really want to come and support the show. But there's plenty of other stuff going on as well. So go to podcastsocialclub.com, check out what's going on, get yourself a ticket and come along. We'd love to see you in the audience on the Friday night. But other than that, even if you just wanted to get in touch with us, there's a bunch of ways you can do that. Emily, how do people get in touch?
So we love Twitter.
We do.
Heart Twitter.
Yep.
At SyzygyPod is us, SYZYGY. And SyzygyPod is kind of our tagline wherever you go.
It is pretty much on the social medias. You can also go to our website, syzygy.fm, and there's a contact form there, as well as all of the other episodes that we've done over the last, we're up to number 48 now?
Yeah,
that's a lot.
this is
We're approaching
exciting.
50. We're going to have to do something interesting with that one. Lots of information on that website. So go and check us out there. But otherwise, that pretty much brings us to the end of the show. So we'll catch you again in about a week's time with some more astronomical goodness. Say goodbye, Emily.
See you later.
Bye, everybody.